Section 8.3, Local Extrema for functions of two variables. In this section, we are going to find the critical points for functions of two variables, and then apply the d-test to classify the critical points for the function of two variables. Local extrema for a function z equals f of xy. Suppose that z equals fxy is a function defined on a region in the xy plane, and the order pair xy is a point on that region. If there is an open region R containing the point AB such that the function value at AB is greater than or equal to the function value of xy for all xy in the region R, then the f at the point AB is called a local maximum of the function f. If there is an open region R containing the point AB such that the function at AB is less than or equal to the function of xy for all xy in the region R, then the f of AB is called a local minimum of a function f. This figure represents the three-dimensional graph or the plane that is the graph of the function of the two variables. As you see the three axes like x, y, and z. The bump here is called the local maximum. Also this one. And then the other two, the dip here is called the local minimum. A point AB in the domain of the f is a critical point if the partial derivative of the f with respect to x at AB equals 0 and the partial derivative of the f with respect to y at AB equals 0. This is the way that we use to find the critical point. If f at AB is a local minimum or a local maximum, then the point AB is a critical point. Note that a critical point does not guarantee a local extremum. In some cases, a critical point gives a saddle point where there is neither a local minimum nor a local maximum. In this case, we're going to use the d-test to identify or to classify the point or the critical point. In this example, we are going to locate the critical point for the function of xy in the form of negative 7x squared minus 5y squared plus 28x minus 40y minus 4. To find the critical point, we're going to find the x and y such that the partial derivative with respect to x equals 0 and the partial derivative with respect to y equals 0 of the given function. That means we are going to first find the partial derivative with respect to x of negative 7x squared minus 5y squared plus 28x minus 40y minus 4. Recall, when we find a partial derivative with respect to x will be treated as the variable, the rest is going to be treated as the constant term. So for the partial derivative of the f with respect to x, we're going to get negative 14 times x plus 28. The partial with respect to y is similar way. We're going to treat the y as the variable, the rest going to be constant. We get negative 10 times y minus 40, and then we let it be 0. And after that, we're going to solve for x and y that satisfy these two equations at the same time. So for f of x equals 0, we work on the equation negative 14x plus 28 equals 0. And then we can see that x equals positive 2. And for the partial of the function f with respect to y equals 0, the equation is negative 10y minus 40 equals 0. This case, we get y equals negative 4. we got x and y that provide the critical point. So we can say that the critical point is located at the point 2 comma negative 4 on the region. And if the problem asks for the critical point for this function, that's including the function value, so the function at 2 comma negative 4 equals negative 7 times 2 squared minus 5 times negative 4 squared plus 28 times positive 2 minus 40 times negative 4 minus 4. It turns out to be 104. That means the critical point on the plane is the coordinate 2 comma negative 4 comma 104. I'm gonna use different colors to highlight this. So this is the x, this is the y, and this is function at xy.